Now, approaching the concept of multi-level signaling, we say that multi-level signaling schemes can be used when we have limited bandwidth. And for that reason, we have been able to show that bandwidth of any modulation system can be shown to be equivalent to 2 FB divided by log base 2 of M. Therefore, if M for BPSK, M was 2, and therefore we could see that the bandwidth was given by 2 FB, because log 2 of 2 is equals to 1. But now when the M increases, when M becomes bigger than 2, definitely, for instance, when we have M is equals to 8, and the bandwidth, this ratio becomes 3, and therefore the bandwidth ratio drops by a third. So we have 2 FB divided by 3. And for that reason, we say that the MRA signaling schemes are very good when we want to conserve bandwidth. So we may have more than one version. We may have MRA PSK, we may have MRA FSK, or we may have MRA ASK, just like we have had ASK in the binary modulation schemes. So the cost of having this increased or reduced bandwidth requirement, or most of the times, comes with increased power requirements. So the power requirements by this modulation scheme increases, whereas the bandwidth requirements decreases. So as we have seen, we may use the MRA to conserve bandwidth, but there are instances when we may use MRA when we may have a channel. For instance, we only require this amount of bandwidth, but we have an extra capacity that we don't use. So sometimes we may use MRA to increase the immunity of the channel from interference or from the error. However, for this work or for this lesson, we are going to focus on using the bandwidth, or we're going to focus on using MRA or multi-level signaling for conserving bandwidth. So we'll demonstrate how we are going to use MRA signaling for bandwidth preservation or utilization. So as we have seen, when we talk about MRA, M may take any value that is of this factor. So we say when the small m is equals to 1, we call that binary because m will be 2. When the small m is equals to 2, we will have quadrature, and that is when we have m is equals to 4. And when m is equals to 8, we'll have the number of bits being equivalent to 3. Therefore, this m represents the number of bits that are used to represent one symbol. And we might also need to mention that the interval of 1 bit always going to be symbolized by TB. And therefore, we say that m represents the possible signal elements. So when we have m is equals to 8, we are saying that we have 8 possible symbols, and which we might be able to represent as 0, 0, 0 all the way to 1, 1, 1. This is representing 0, this is representing 7, or the 8th symbol. So we are saying that because it is able to talk about PSK, we are saying that we are carrying the information on the face of the carrier. So we are going to be varying the face, and as we have already said, the information is going to be carried by this data I that we are varying. This is a normal carrier with the amplitude as indicated. This figure is always used to allow us to get normalized power. So for the purposes of this discussion, we're going to be focusing on the value of this theta I. So theta I may be symbolized as being a ratio of 2 pi I divided by m, and m, in our case, we can start with the m being 8. We say that when you say 2 over 8 pi I is increasing from the value of m from 0 to m minus 1. So in our case, when m is 8, this will be 7. So we are starting with 0, 1, all the way to 7. So for the first one, definitely the value of theta I would be 0. When I is equals to 0, our theta I is going to be equals to 0. But when I is equals to 1, our theta I is going to be given by 2 pi times 1 divided by 8. That is equivalent to 4. That is pi over 4, which is equivalent to 45 degrees. So our signal is going to be varied in phase by 45 degrees. So this equation therefore is used to represent the 8 array or M array PSK, and therefore what we are varying is the phase that we of our carrier signal. So we notice that it's possible to transmit more than 2 bits at a time using multiple different phase angles, resulting in multi-level PSK. And we actually see that one of the most common modems that transmits at 9600 BPS uses 12 phase angles, 4 of which have the same amplitude, and the total of them we are able to get 16 different signal elements. So PSK is a very significant modulation scheme, particularly when we are using M array being more than 2 bits or more than 2 sables. So now talking about the modulator, we say now that the modulator can be a little bit complex, but superficially we may be able to describe a very easy way in which we are able to form the M array PSK signal. The first step is to receive the binary data sequence that enters into our serial to parallel converter, and this can definitely mean that the output data, while it is arriving at the rate of FB, which is equals to 1 over TB, it is going to be output here at a rate of B divided by M. So there is higher rate of binary input, but the output is coming at a slower rate because they are first of all getting arranged into a parallel form, and therefore they are output to our digital to analog converter. So that is the first thing, that the period in which, or the rate in which these sables are getting released from the serial to parallel converter is actually FB divided by M. So after we have got our parallel conversion of our bit binary sequence, these bits are fed into a digital to analog converter that produces analog pulses that are equivalent to the symbol that was sent. So for instance, if we have received, I think here this is incorrect. So here you are saying that the M is a small m. So in this case for 8 array, so the small m is equal to 3. So we are saying that one symbol is represented by 3 bits. And for that reason, we are going to be having 0 to 2 bits arranged as such. Therefore, these bits are going to be fed into a digital to analog converter. So for instance, if we have received 101 equivalent to 5, that means you're going to be generating an analog voltage that is equivalent to symbol 5. So when it is equivalent to symbol 5, that analog voltage is now fed into our sine wave generator, or that is controlled by this analog voltage, and this analog or this sine wave generator is the one that produces a constant amplitude sine wave, but with varying phase. So what we notice is that constant frequency and amplitude and frequency are constant, but it generates a signal or a carrier signal that is varying in phase depending on the voltage that has been generated. So if we have generated an analog voltage for 5 volts, then we are going to be producing a signal whose phase is representative of number 5. So for instance, we had said number 1 is equivalent to 45 degrees, 0 is equivalent of 0. I'm not sure how much 5 is, but if it is, for instance, it is 270, then we are going to say that the signal or the carrier signal that is going to be generated is going to be out of phase by 270 degrees, and for that reason we are able to have a constant amplitude and frequency with varying phase M array PSK signal that can now be used to transmit our binary data sequence. So in summary, that is what we have just said, that the operation of PSK operates as follows: that the serial to parallel converter can store M. M we have seen is the M that is here, the small m. This is the number of symbols. These are the number of bits. So we're saying that this m is the number of bits, which represents one symbol, and therefore they are supposed to appear in parallel at the output of the serial parallel converter. And we have seen that the period of generating those symbols is equivalent to m times tb, which is the symbol duration. And the output of serial to parallel converter remains unchanged for t seconds. After every t seconds, we are able to have the output of a given symbol. And then we are saying that that output produces a constant amplitude sinusoidal output voltage, but phase is the one that is varying dependent on the output that we want, and that is the output that we send to our digital to analog converter, and the phase will change only once per symbol period. So that is in essence the introduction to MRA PSK and even the modulator for that PSK signal.